Here in this video, we're going to look at finding the derivatives of inverse trig functions. And we're actually going to derive some of our derivative rules here. And knowing this process of how to derive these rules can be helpful in case you forget them. But it also reinforces a technique we learned a little earlier, which is the implicit differentiation process. And so what we're going to do is we're going to start here with y equals the inverse sine of x, and we want to determine what is the derivative of inverse sine. Now note, you cannot use the power rule here because that exponent here means inverse sine or arc sine, not sine to the -1 power. Now the process to start this is we're going to use the fact that if I have inverse sine of x equals to y, that means that if I was to apply sine to the y function, that would equal x, because the inverse just unapplied sine to y. And from here, we're going to take the derivative of both sides. And the derivative of both sides, let me change colors here, would be the derivative of the left, derivative of sine is cosine. So it'd be cosine of y. dy over dx is equal to 1. And I would divide cosine over, and so the derivative of y with respect to x here so far is equal to 1 over cosine of y, or just secant of y. And how does that help us? Well, the problem is we started with having an explicitly defined function where I had only x on the right, and now I have a derivative that is in terms of y. So we're going to use a technique from pre-calculus here where we're going to create a right triangle based on the fact that if I apply sine to y, in this case angle y, it is equal to x. So I'm going to construct a right triangle. And I'm going to put y in as to one of the angles. So here's y. And if I apply sine to that angle, I have to equal x. Well, sine is opposite over hypotenuse. So the opposite side will be x. The hypotenuse side will be 1. And let's go ahead and find the missing side using Pythagorean's theorem. So the missing leg would be 1 minus x squared. Now, we go back and say, all right, well, our derivative of y with respect to x is equal to secant of y. Well, secant of y, in terms of right triangle trig, will be hypotenuse over adjacent. So dy over dx is going to be equal to 1 over the square root of 1 minus x squared. So that is the derivative of inverse sine. Now let's do the same process here for inverse tangent. So I want to find what the derivative of inverse tangent of x would be. Now, remember that if I turn around and apply tangent to both sides, I'd have tangent of y is equal to x. And if you wanted to, here, we could go ahead and make that right triangle that we did before. We kind of get an idea of where this is going. And so I construct a right triangle such that if I apply tangent to angle y, I get x. Well, tangent is opposite over hypotenuse. So opposite x, hypotenuse 1, that maintains my ratio of tangent of y equaling x over 1. And let's go ahead and find the missing side. So Pythagorean's theorem, missing side would be the square root of the sum of the two legs squared. So 1 squared plus x squared, square rooted. So we go back to our equation, and now we take the derivative of both sides with respect to x. So the derivative with respect to x of tangent of y equaling the derivative with respect to x of x. Well, the derivative with respect to x of tangent of y, you have to do the chain rule. The derivative of tangent is secant squared. So it'll be secant squared y times the derivative of the inside, so dy over dx, is equal to the derivative of x is 1. Well, I divide the secant squared to the other side, and that would give me dy over dx is equal to 1 over secant squared y, which is the same thing as cosine squared of y. Now you go to your triangle and look at your trig ratios and figure out what cosine of y would be. Well, cosine of y is equal to adjacent over hypotenuse. So this 1 over the square root of 1 plus x squared, where I need to square that. So our derivative is going to be that function squared, so it'll be 1 over 1 plus x squared. So the derivative of inverse tangent of x is equal to 1 over 1 plus x squared. And let's do one more. We have inverse secant. So we continue this process on. So I would apply secant to both sides to rewrite this without an inverse function. Secant of y is equal to x. We're going to derive this by creating that right triangle again, such that if I apply the secant function to angle y, the ratio of sides is x. Well, secant is hypotenuse over adjacent. So the hypotenuse would be x. The adjacent side will be 1. To make that ratio happen, we find the missing side. So the missing side will be the square root of hypotenuse squared minus leg squared. And now we go through and we'll find out what our derivative is. So we'll take the derivative of both sides. So the derivative with respect to x of secant of y equal the derivative with respect to x of x. Well, we're doing the implicit differentiation process. So I take the derivative of the left-hand side, the derivative of secant of y. Do the derivative of the outer function first. That is secant y tangent y times the inner function dy over dx equals derivative of x is 1. And we can move everything over to the other side. And we do that, we'd have dy over dx is equal to, we'd have 1 over secant of y tangent of y. Now, if I clean that up a little bit, what that would be, 1 over secant, same thing as cosine, so it'd be cosine of y, times tangent of 1 over tangent, same thing as cotangent, so cotangent of y. So that's my derivative line here. Well, to figure out what those are, we go back to our triangle that we formed. Cosine, when applied to my triangle, adjacent over hypotenuse, 1 over x. Now, here's the thing to remember, is x being the hypotenuse, x is always non-negative in this case. So it would be the absolute value of x. Cotangent of y, cotangent is adjacent over opposite. Now we go back into our derivative line and we put those two things where they go, and we multiply those two rational functions. We have 1 over the absolute value of x times the square root of x squared minus 1 being the derivative of inverse secant of x. So I've summarized, we have derived, we use proofs to show what all of these derivatives are for those three trig functions. Inverse sine, inverse tangent, inverse secant are the three most common inverse trig functions you'll use out of the 6. And what you'll notice is when you compare their derivatives is that the difference between inverse sine's derivative and inverse cosine's derivative is just a negative. Same thing with inverse tangent and cotangent. Cotangent's negative, and inverse secant and inverse cosecant, the cosecant's negative. An easy way to remember this, all of the cos are negative. Cosine, cotangent, cosecant are negative derivatives for their inverses. So I have 3 examples here. Let's apply these derivative of inverse formulas to find these derivatives that are listed here below. So let's find the value or the functions, the derivative expression for inverse sine of t squared. Now we're having to apply the chain rule because we have t squared instead of just x. So what we're going to do is we'll start with the fact that we're going to take, let's say we have inverse sine of u. Now, inverse sine of u, if we take the derivative with respect to x of inverse sine of u, that's going to equal, it'd be 1 over the square root of 1 minus u squared, so that's the derivative of the outer function, times the derivative of the inner function, du over dx. Our chain rule. Well, instead of u, we have t. So our derivative is going to be, we'd have 1 over the square root of 1 minus. Now, it should have been x, but it's not x. Now it's t squared. So it'd be t squared squared. And then times the derivative of the inner function, which makes 2t. And then you just clean that up a little bit. We'd have our derivative would be 2t divided by the square root of 1 minus t to the 4th power. Let's do another one here for inverse tangent. So some people like to rewrite this in terms of an inner expression. You don't have to do that. I mean, you could define u as being the square root of x minus 1 and rewrite your problem where you want to find the derivative with respect to x of sine of u, or excuse me, inverse tangent of u, and which means when you did the chain rule, that would be 1 over, inverse tangent's 1 plus x squared, so it'd be 1 over 1 plus u squared times the derivative of u with respect to x. You can do it this way. And the derivative of u with respect to x, well, you just differentiate your u equals equation, which, remember, the square root of x minus 1 is really x minus 1 to the 1/2. And so that would be 1/2 times x minus 1 to the negative 1/2 times the derivative of the inside, which is 1, which is basically 1 over 2 times the square root of x minus 1. And I would just put all of this in to our expression. So that was du over dx. And then you'd go back and change out the u for the square root of x minus 1. And so our derivative of inverse tangent of the square root of x minus 1 would be 1 over 1 plus the square root of x minus 1 squared. I got one too many parentheses here. Times 1 over 2 times the square root of x minus 1. And some minor simplification. We'd have, that would make 1 over, we'd have x, so it'd be 1 over 2x square root of x minus 1. Okay, last one here, we want to find the derivative of x times inverse secant of 3x. Now, we actually have to do product rule because I have x times inverse secant. So we would do first times the derivative of the second plus second times the derivative of the first. Okay, well, basically we'd have x times, and let me color code here a little bit, the derivative with respect to x of secant, inverse secant of 3x, plus, derivative of x is 1, so plus the inverse secant of 3x. So I need to figure out that green section here. Well, if you wanted, we could look at this as saying that the derivative with respect to x of inverse secant of u is going to equal, we just change all of our variables in our secant equation to be, our secant, inverse secant derivative to be used, would be 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of the inner function with respect to x, du over dx. And what we have done is we've replaced u, or u is representing 3x, so that means du over dx is the derivative of 3x, which is just 3. And then you can put all that in and say that the derivative of inverse secant of 3x is equal to 1 over the absolute value of 3x times the square root of u squared, which would be 9x squared, minus 1 times 3. All of that here, when I simplify it, goes right there in green. So our final answer for our derivative in this problem is kind of a mess. All right, well, one thing I know is that the 3 there is going to cancel with this 3 in here. We would have, and I'm going to put it all back up in this problem there. So we'd have x over the absolute value of x times the square root 9x squared minus 1 plus inverse secant of 3x.